Okay, so for this one, we're going to be talking about not just solving equations, but actually what properties allow us to solve equations. And then I'm going to use that as an opportunity to review not only those properties, but also, solving some challenging equations that maybe you haven't seen yet, or maybe you should have seen. But, well, let's take a look. So a couple of quick activators here. Um, we're going to review set notation. We're also going to review um, just solving in general. So for this first one, we have to subtract 12 from both sides in order to isolate our x. So we get -10. By the way, it's a good idea for you guys to pause the video and then try these problems out on your own and see if your answers match mine. Now, for set notation, we're not just going to leave it as x equals -10. We're going to write it with these curly brackets as -10 like that. So that's the fancy way of doing set notation. On the next one, we have 3 plus x. It's on the right side. Sometimes students are like, what? X on the right side is supposed to be on the left. It can be on either side. We're talking about an equation. Left side and right side are equal, so it doesn't matter. I'm going to go ahead and subtract 3. And again, I'm going to write it as a curly bracket. In the next one, we're going to subtract 3 again. Okay, because remember, we talked about this the other day. We're going to go in the opposite order of PEMDAS to solve this. So we're going to start with the addition and subtraction of 3 here, the constant. That 3 is positive, so I'm subtracting it. So you get -12 is equal to -x. It's like there's an invisible 1 in front of the x. So really what we're going to be doing here is dividing each side by -1. So I end up with x equaling 12. And again, my curly brackets. That's all set notation is for now. In the next one, we are going to have a fraction in front of the x. So what we can do is multiply by the reciprocal. So I can multiply both sides here by -5/4 to cancel out the negatives, and to cancel out the fraction. Because the 4's would cancel, the 5's would cancel, leave me with x on the left side. And I'm going to get a fraction on the right side. I got to simplify that fraction up. So you could either think of it as 30 over 4, which reduces down to 15 over 2. Or if you're comfortable doing this, you can actually cancel out anything. If you're multiplying, you can cancel out anything in the numerator with anything in the denominator because they're opposites of each other. So I could have canceled the 6 and the 4 and been left with a 2 and 3. And then 3 times 5 is 15. And the 2's would cancel as well. So we end up with 15 halves. Now, again, my curly brackets, 15 halves. Okay. The next one, I'm going to subtract 11 for both sides. Divide both sides by 4. I get x equals 4, so I'll have a curly bracket there. For the next one, subtract 14 from both sides. So again, I am working the opposite order of PEMDAS, starting with addition and subtraction. That 14, even though it's not subtracting 14, it's subtracting x. So it's a positive 14. We're going to subtract 14. We get -x is equal to 6. So that means if we divide both sides here by -1, we get x is equal to -6. And notice, guys, that like my fancy curly bracket here isn't perfect. That's okay. I mean, it should be, but it's fine. For the next one, we have two options here. We can distribute the 2. We could also do the opposite of distributive property, which is division. Distributing is multiplying. So I could have actually started off by dividing both sides by 2, which would have given me -4 on the right side, and it would have canceled out this 2 here, and I would have had smaller set numbers there to work with, but well, let's keep it going. So I'm going to do what you all would probably do, which is distribute. And that's fine too. So now I'm going to go ahead and add 12 to both sides. Divide by 2, and I get x is 2. In the final example, I'm going to give myself a little bit of space to do this one. So if I go ahead and do this again, I'm going to do what you all would do, which is probably start by distributing, although you could multiply by the reciprocal on both sides and cancel that 2/3 out. But I'll do what you would all probably do. Now, when you multiply a fraction times a whole number, like we are here, or an integer, integers and whole numbers are basically the same thing. So 2/3 times 6, we can actually divide by the denominator and then multiply that by the numerator. So 6 divided by 3 is 2, and 2 times 2 is 4. Next, we'll go ahead and add 4 to both sides, and now we have to deal with this fraction in front of x. That's the coefficient. The coefficient is a fraction, so we're going to multiply by the reciprocal. And again, I can do the integer times the fraction. I can do 4 divided by 2, get 2. 2 times 3 is 6. All right. That should have all been review. If it's not, I would encourage you to, see me. All right, let's go ahead and tackle this one. It's another activator problem. It's one that we saw already. How to handle a variable on both sides. So if you recall, 4x is like having 4 lengths that are the same on one side. And on the other side, we have 3 x's. So we have 3 of the same lengths. I can just go ahead and essentially cancel out these 3 lengths with 3 on this side, and I'm left with one single x. So what we're essentially doing here is not dividing by 4 or dividing by 3. Instead, we are essentially subtracting, and I would subtract the lower coefficient, but we're subtracting from both sides one of the variables. And now I'll deal with the constant. Now, does it matter if I deal with the constant or the variable first? Um, Not necessarily, but yes. It doesn't matter in this problem. You could tackle the x's first. You could have tackled the tens first. But the reason that I did it with the x's first is that there may be problems where that doing the constant first can lead you to a special solution that you then get confused by. So I always tell students, start with the variables. When you have a variable on both sides, move them first, then do the constant. So I like to do it this way. So we've all heard, whatever you do to one side, you must do to the other. And this is true, but it's not really mathematically sound language. The correct language is that we have two properties: addition property of equality and multiplication property of equality. And what that essentially means is if you are subtracting something from both sides, you're doing the addition property of equality. Subtracting or adding. If you are dividing or multiplying both sides by something, you're doing the multiplication property of equality. Because division is just multiplying by a fraction. So let's see where this falls into. We're going to solve this equation, but we're going to justify each step that we do. So in the first step, I'm going to do what you would all likely do, which is distribute. And so that's my first step. My first step is distributive property. So how am I going from step 1 to step 2? I'm going to use the distributive property here. Apologies for my handwriting. So I get 4x plus 8, and then I'll bring down the rest of the problem. Now, what's the next thing all of you would likely do? Probably combine your like terms, but before we do that, we actually want to put those like terms next to each other. So I'm doing this probably in more steps than you might do it in, But that's to show you all the different properties. So I'm going to switch around these two. Switch around. What property is that? That's commutative property. So how did I go between these two? I used that commutative property of addition. And then I'm going to go ahead and I'm going to combine my like terms together. So that's going to give me 4x minus 2x. That's 2x. So how did I go from this step to this step? I used like terms. Next, we're going to go ahead and subtract x from both sides like we did on the previous slide. But this time, what property am I using to justify that? I'm using the addition property of equality. I'm abbreviating here because of my, it's a little hard to write on here, but it's the addition property of equality. Finally, I can subtract 8 from both sides and end up with x equal to negative 3. What property did I use for that? I used the addition property of equality, the same property I used on the last one. So that is how you justify each step. Okay, we're actually going to skip this one and come back to it in class. So let's go ahead and tackle this last example here. Um, without solving, let's explain why the following two equations have the same solution set. So we're not going to solve these and show that they're both x equals whatever. Instead, we're going to talk about what's commonly referred to as scaling up or scaling down. Um, do you notice that 4x and 2 and 5x and 3 are multiples of 6, 12, 15, and 9? Specifically, if you multiply all of these ones on the left by 3, you'll get everything on the right in a slightly different order. So what we're going to do instead is we're actually going to show that the left side and the right side between the and sign are the same. So if I start with the left side, to get it to look the same as the right side, I'm going to start by actually moving the 4x and the 2 so that they're in the same order as they are on the right side. So what's switching that order around? What property is that? That's commutative property of addition. Next, I'm essentially going to scale this all up. So I'm going to multiply this whole equation by 3. So I can do that as long as, again, whatever I do to one side, I do to the other. So if I multiply them all by 3, the reason I'm allowed to do that is by the multiplicative property of equality. So I didn't actually solve for x. Instead, I now showed that the left side and the right side are exactly the same by using those properties. And that's the same thing. That's called scaling up or scaling down. All right, guys, I'll see you in class tomorrow.